Okay, in your notes, turn to page 16 and inspect these two nuclei. Well, you've got proton, neutron, neutron. They bind together, they form a nucleus, and in total, 9 mega electron volts of energy is lost. Okay, down here you have 3 of each. This is actually a lithium-6. Lithium-6 is this nucleus. They all, bam, they come together. They form a nucleus, they bind. And they lose energy when they bind. And in total, it's going to be 30 mega electron volts. So what's the binding energy for this first nucleus? What's the binding energy for the second nucleus? And what's the binding energy per nucleon for the first nucleus? What's the binding energy per nucleon for the second nucleus? Take a moment, pause the video, answer these questions. Well, binding energy is just the total energy lost when a nucleus forms from free or individual nucleons. So what's the total binding energy here? It's just 9 mega electron volts. And what's the binding energy for this nucleus? Well, it's the total that you lose, which is 30. We could take the 9, we could split it up for the 3 nucleons, and each one would get 3. That's the binding energy per one nucleon. Down here, the binding energy per nucleon is 5. We take the 30 total, we split it up across the 6 nucleons. Now, what we're reminding ourselves of is that when you bind the nucleus together, mass gets lost. What happens to it? It converts to energy. Specifically, it converts to a gamma ray photon. So that's tons of energy. That's a super high energy photon. And you don't normally, this is kind of an inaccurate picture. Normally, we're not actually emitting 3 different photons. What we typically see is one single gamma ray photon with all 9 MeV. Same thing down here. We would really only have one gamma ray photon with all 30 mega electron volts. So looking at the picture, when you compare this very small nucleus to this small nucleus, what's the pattern? As you increase the size, how does that change the binding energy per nucleon? Answer 14. Well, as you get bigger, what happens to the binding energy per nucleon? Then I want you, using E equals mc squared, explain why that bottom nucleus, the lithium-6, why does it have a higher binding energy per nucleon than the top one, which is hydrogen-3? Think about the nuclear attraction, right? Think about, okay, which of those nuclei is a bigger magnet? Stronger force, nuclear force, that means something about potential energy, more potential energy. And then if you have more potential energy, then you lose more, there's more energy loss in order to bind as a nucleus. And more energy loss means more mass lost. Oh, but we're not energy loss. That's it, we're done when we get to energy loss, because the energy lost is the binding energy. More binding energy. Now we move on to the binding energy curve. If binding energy is the most important definition of this unit, this graph is absolutely the most important graph. First, let's inspect the axes. The x-axis is A. All of them. It's all of the nucleons in the nucleus. Protons and neutrons both. So if we look at the left side, helium-3, that's, 2 protons and 1 neutron. And as we move to the right, okay, well, here's helium-3. It's this nucleus. Here's lithium-6. That's the one we saw before. That's 3 protons and 3 neutrons. and you move to the right, farther and farther to the right. Here's xenon 130. I'll spare you from actually drawing 130 nucleons. But imagine that's 130, and we keep going to the right, and they just get bigger and bigger and bigger. All right? So what's the y-axis? It's the binding energy per nucleon in mega electron volts. It's this value. Oh, let's check and see how good my example was. Lithium-6 has 5 MeV, I said. Is that accurate? Let's go find lithium-6 and find its binding energy per nucleon. Okay, how good was my example? Here's lithium-6, and hey, 5.3, 5.4. That's not too far off. What I want you to do is put a box around the most stable nucleus that you see. And remember, stability is measured using binding energy per nucleon. It's measured with the y-axis of this graph. The higher up you go, the more stable the nucleus. And lower down is less stable. If you want a visual picture, here's the picture. If you want to knock free a single nucleon, the helium-3 only takes 2.5 mega electron volts. If you want to knock free one of those nucleons, how much energy do you need? You need about 5.4 mega electron volts. If you want to knock free one of those xenon, how much energy do you need? Well, I didn't get that one. What is it, 8.2 or something? You need to blast it with 8.2 mega electron volts to knock free just a single nucleon. So stability we measure using binding energy per nucleon. So what's the most stable atom? Well, according to a nucleus, according to the graph, it's iron 56. If you move to the left or to the right, you decrease in both directions. To the left of iron 56, binding energy per nucleon decreases as we decrease the size. And to the right of the graph, again, it decreases as this is just flipped, isn't it? If you move to the right, you're increasing the x-axis. So why is that? Why is it a decrease on both sides? Well, if you move to the left and you get smaller nuclei, well, for those nuclei, those nucleons are all close enough that the short-range nuclear force dominates the long-range electric force. So when you move to the left, you have fewer nucleons. Fewer nucleons equals less nuclear force. It's a weaker magnet, so to speak. And less nuclear force means less PE to lose when you bind, when binding. Less binding energy, in other words. But if you get bigger than 60 nucleons and you keep going past that value, bigger and bigger and bigger, now the nucleus is really large. Some of the protons are distant enough, they're far enough away, that electrostatic repulsion, the Coulomb repulsion, dominates the attractive nuclear force. So you've got 60 already in here, and you keep piling more and more in. Well, you're just adding more protons to repel the protons on the other side. So you're actually increasing the repulsion and kind of making the nucleus less stable. All right, let's estimate the total binding energy, and the word total is redundant. It could just say estimate the binding energy, and it's asking the same question. For xenon 124, well, we already kind of looked at this. Xenon, did I look at this? 124. Let's put an S above that stable nucleus. Xenon 124, here it is. That's it right there. I trace over. And I'm going to call that 8.3 mega electron volts. So that's 8.3 is how much I have to blast to remove one of the 124 nucleons. If I want to remove them all, if I want to totally separate the nucleus into free nucleons, then I have to take that 8.3 and multiply by 124. And that gives me the total binding energy for the entire nucleus, which is, let's say, 8.3, times 124. Okay, since we're estimating, we'll call that 1,030 mega electron volts. Which has more binding energy? The word total is redundant. They won't say that on an IB test, but they do mean total. It's implied by this term. Which has more, U-235 or platinum 194? Okay. Uranium 235, where's that? Oh my gosh, it's all the way at the end. So what's that value? 7.4, I'll guess. My estimating's not always the best. Or, what was the other one I was doing? Platinum 194. 194 platinum, there it is. We trace over. I feel like I got too high. I think that was supposed to be more like 7.8. All right. The binding energy for uranium. And then we'll do it for platinum. Well, for every one of the uranium nucleons, it's 8.3 MeV. No. What was it? 7.3? 7.4, I think I said. And how many are there? How many nucleons are there? 235. $17.39, which just so happens to be my PIN number for my bank account. It's funny. All right, how about the platinum? Well, we said that was a little bit more energy needed to knock free one of those guys, but we want the binding energy for the entire nucleus. So this is the amount for one nucleon, but platinum has 194 nucleons in its nucleus. So what do we get? 194 times 7.8, 1513.2. So which has more? Well, uranium. But which one is more stable? Platinum is more stable because it has a higher binding energy per nucleon. That's interesting. U-235 has more binding energy. That nucleus does. But it's still less stable than, what's the other one? The platinum 194. Because it has, whoa, how do we still, I was thinking about the word less. It might have more total binding energy, but it has less binding energy per nucleon, per individual nucleon.